So I've been talking about this idea of long-run regularity or long-run patterns, and we're trying to contrast that with what would happen in the short run. And I just wanted to clarify what I mean by these things because again, I'm going to use this language more moving forward, and I want to make sure that everyone is on the same page. So probability again tells us that randomness is regular in the long run. It also tells us that random phenomenon is not necessarily regular in the short run. So let's look at what we mean by that. So I'm going to show you some outcomes of 5 coin tosses. I'm going to show you 4 different possible outcomes, and I want you to think about which outcome you think is most likely to occur. So again, we're just tossing a coin 5 times and we're looking at the outcomes. So here we are. So 1, 2, 3, and 4. Which of these do you think would be most likely to occur if we toss a coin 5 times? Now I'm hoping that you're thinking again of the fact that 5 times is really not that many times. 5 times would be the short run. We're just looking in a very short series of repetitions of what would happen. And remember, in the short run, random phenomenon is not necessarily regular. So it turns out that all 4 of these outcomes are equally likely to occur in the short run. You might be looking at things and you might be thinking, well, it would be unusual to see 5 in a row of the same thing. Maybe you were focusing more on this third option as being what you thought would be most likely because to you it looked like it was random. So remember, random means what we'd expect to see in the long run, not in the short run. So over time, if we kept on tossing the coin, what would we see? So this again is just a very short number of, or a very small number of trials. And to kind of drive that point home more by what I mean in the long run. So again, if we toss a coin many times, we might see several of the same outcomes in a row. Okay, so over time, you might see several of the same outcomes in a row. If we go back to what we just looked at, these different sets of outcomes were really just taken out of context. They're little snapshots of what we might see if we just pulled out 5 different outcomes from a series of lots and lots of other outcomes. So over time, across a long run or a long series of tosses, we would expect to see that 50% of the time we have heads, or we have 50% heads and 50% tails. And so this is kind of what I tried to put together to show you what I mean by the long run. So what I did here is I used different colors to differentiate heads and tails. And as you're looking at this, many different coin tosses, you'll see that sometimes we do have a lot in a row of the same outcome. That doesn't mean that there's something wrong with the coin. If we keep tossing, we're going to see that things are going to even out over time. So there are other times when we have a lot of heads. Here's a long string of heads. So that doesn't mean the coin's unfair. It doesn't mean it's weighted in a certain way to give you more heads or more tails. So each time we toss the coin, we're going to see, we don't know exactly what's going to happen, but over time, in the long run, if we look at lots and lots of outcomes, we're going to see a pattern. That is what randomness and probability are all about. Seeing a pattern emerge over time. What's that pattern going to be? Now, there's something you're learning about in Chapter 17 called the myth of the law of averages. And I've linked up here to a video about something called the gambler's fallacy. So the myth of the law of averages is also sometimes referred to as the gambler's fallacy. And I hope you'll watch this video to learn a little bit more about this and to really solidify some of the ideas that are coming up in Chapter 17. So let's say again that you flip a coin 9 times and you get the following results. So 9 times you toss this coin. Every single time you get a tail. What's going to happen now in the 10th toss? Are you thinking, I'm due for a head? I've had so many tails, it's got to be a head this 10th time? Or are you thinking, well, it's got to be a tail because I had so many tails in a row? Or are you thinking it could be either? There's a 50% chance it would be heads and a 50% chance it would be tails. I'm hoping you're thinking that last thing, that you still have just a 50% chance of getting heads or tails. So each time you toss the coin doesn't remember how it landed the time before. Each toss does not affect the next toss. So each time you toss the coin, you have a 50% chance of getting a head and a 50% chance of getting a tail. So even if you got a long string of one particular outcome in a row, that doesn't make another outcome more or less likely the next time you toss. And this is known as the gambler's fallacy, just because, a reason some people will bet a lot when they're gambling is because they think that the outcomes that occurred before are somehow related. That if they had a string of bad luck, that all of a sudden they're due for some good luck. Or maybe if they've been really lucky many times in a row, they think that's going to continue, so they bet big. So they're thinking about what's happening in the short run. They're being tricked into this myth of the law of averages, and they're not really thinking about this idea of long run patterns of what we would see emerge over time. So this next slide I put in here for one specific thing. So we've been talking a lot about coins now, about how there are two sides to a coin, and if the coin is weighted properly, each side is not more likely to occur than another. But I don't want you to get tricked into thinking that if there are only two options or three options or four options, that each option is equally likely to occur. So are babies like coins? So does each gender have the same probability of occurring? And so it turns out actually that if you look at some research, it's a little bit more likely to have a boy than a girl. Not much, but a little bit more. So two outcomes, but they're not equally likely. So remember that. Remember that if you have a certain number of outcomes, they might not each be equally likely. Think about die rolling. So here's another example where we roll a die. Each time you roll a die, there's a 1/6 chance of getting any of the different sides of a die, any of the different faces, if it's a fair die, if it was created in a way to be fair. And so this is what a die looks like. These are all the different faces. And again, we know there's a 1/6 chance because if we roll the die over and over again and look at the outcomes and look at that long run pattern, we'll see that no one number occurs any more frequently than others. I did put actually a little link here for those of you who might be interested. There was a story that came out not long ago about how dice are fair today, but that wasn't always the case. So anybody who might be interested in some history or trivia, I hope you'll look at that. So again, here's a case where we have 6 different outcomes, and it turns out in this particular example, each of those outcomes is equally likely. Are pigs like dice? So what do I mean by that? So not everything that is random with 6 options has a 0.166 probability for each option. So 0.166, that's equal to approximately 1 in 6. So by what I mean by pigs, I don't know if any of you have seen these pigs before. These are 2 little rubber pigs that you can toss around. There's a game out there called Pass the Pigs, and you toss these 2 pigs, and they can land in 6 different ways. And basically you get certain numbers of points based on how the pigs land. You can lose all your points if they land in a certain configuration. And I like to use this example because unlike tossing a die, when you toss the pigs, even though there are 6 different options, each option is not equally likely. Here are actually the ways that the pig can land. So that each way has a particular name. You'll notice there's a little dot on one side of the pig, and on the other side there's no dot. So the pig could land with the dot side up. So it lands on its side with the dot side up, or it might land on the other side with no dot. It can land standing up, it can land on its snout, it can land on its ear. So each of these different landings has a particular name and a certain probability. So you'll see it's very unlikely that you're going to get something called a jowler where it's leaning on its ear. It's much more likely it's going to land with the dot up or the no dot up. So again, just because we have a certain number of options, each option is not equally likely. Now chapter 18, so I'm kind of going between chapters 17 and 18 a little bit here. I wanted to talk a little bit about some of the content in the first part of chapter 18 because I feel like it relates a lot to the ideas that you're learning about in chapter 17, and I feel it has a place here in this particular lecture. So we want you all to have an understanding of different rules related to probability. So if you're given a set of probabilities and you have to determine are these legitimate probabilities, there are a couple things that you're going to want to look at. First of all, you want to make sure that each probability is a number between 0 and 1. That's very important. If you're given a negative probability or you're given something like 2.7, you know those cannot be correct because probabilities cannot take on those values. If you're looking at a bunch of different outcomes, for example, when we looked at rolling a die, the different outcomes are those 6 different faces. If we add together the probabilities of each of those different faces, those outcomes must sum to 1, must add to 1. So again, these two things together, if we ever ask you, is this probability model legitimate, we want you to look at those two things, that each probability is between 0 and 1, that all the probabilities together of all the possible outcomes in whatever the event is that you're looking at, that they all sum to 1. Some other things that are going to be important and that can help you solve problems rather quickly: the probability that an event does not occur would equal 1 minus the probability that it does occur. So we might ask you, what's the probability that you roll a die and you do not get a 6? Well, it would be 1 minus the probability that you get a 6. And we'll practice these different rules in a moment. If two events have no outcomes in common, we call those events independent. And if they have no outcomes in common, the probability of one or the other occurring is the sum of their individual probabilities. And I should have actually said 2 or more events here, because you don't have to just be focused on 2. You could be focused on 3 or more. So essentially, if events are independent and you want to know if one or the other occurred, or if multiple events are occurring, you would just add together the different probabilities. So again, I'm going to stop now, but when we come back, we'll actually work through some problems where we'll apply these rules, and you can see how you'd actually use the rules and what kind of problems would require that you use those rules. So we'll be right back, and hopefully we can try to wrap things up in one more video.